meeting is being recorded.
Yeah. So assuming all these things and flight time of 45 minutes again, very bad. This in a regular air transport will take about 4 hours for a distance of about 250 kilometers. Whereas if you take, there are some configurations that are already working on VTOL taxis, eVTOLs, there's the Lilium jet, that would take 1 hour 13 minutes. So it is a time saver. And time saving is very, very important, very critical when we come to organ transport. Okay, no? 1 second. Yes. It is. Yeah. So if you look at the organ transplantation scenario in India, worldwide, yes, it is, of course, there, but even considering the India, nearly 50,000 people are in need of heart transplant, and about 3 lakh for kidney transplant, and more than 1 lakh waiting for liver and corneal transplants. So one of the existing methodology is to create green corridors, which is, of course, in the absence of any other alternate, this is the only way. So they create what are called as the, is to cater to things in that golden hours. It is very essential that you have a corridor like this. But considering the situations in the city, it is not always easy to do this. Even creating green corridors. In fact, when we were discussing, one of the, I forgot the name of the doctor, but when they were carrying even in this road ambulance, the heart transplant, the ambulance with traveling in a green corridor with zero traffic, hit against a divider, and they had a lot of problems. So anyway, road transport is really not all that easy. And the National Organ and Tissue Transplant Organization puts it on record that at least 3 hearts got lost in Indore, while 1 each at various medical institutions in Jaipur, Aurangabad, and Surat, Chandigarh, and Pune. And 2 livers got wasted in PGI Chandigarh. So this is something very, very serious. So something has to be done to ensure that we don't actually lose on the organs that are available and reach us in time, because preservation of these organs is a very, very critical issue. Also, when they get to know that, okay, for example, heart is available, let us say in Chennai, and somebody in Fortis Hospital in Bangalore is ready to, as the recipient, then before the heart actually arrives, they will start preparing the patient. Patient preparation includes cutting open of the chest. So it is such a critical thing. So in the meanwhile, if that does not reach on time, it's a very serious thing. And you can see some of the statistics on the right side graph. As on 2018, we have the actual deceased organ donors who are deceased, they're there, and then diseased transplants, and then the living transplants. So the numbers are quite, you can see on this left side, they are in thousands. So quite large in number. So this has to be catered to using the technology. Also considering the problematic areas, for example, the Northeast, we have been focusing on Manipur, for example, where the medical service accessibility is very, very poor because of the topology. As you can see down below, the variation in the altitude, all the way it can go to about 2,600 meters. And the terrain is highly uneven. The roads networks are very problematic, poor connectivity. Then, of course, hilly terrain. Then the communities having very limited means of livelihood, and it's very essential that we provide some technological support to such things. And we know that the government is also interested in catering to the health related services in such areas. So considering all these things, we are trying to design a holistic system. Holistic systems, we mean it is the VTOL, which can carry the human organ and also the transportation box for carrying the transplant. That's also very, very important. When we talk about the organ itself, you see this, there are a lot of issues. For example, the problems could be inability to maintain the required temperature gradient. If it is not maintained, less or more would definitely impede the performance of the organ to be transplanted. So one has to maintain. In fact, ideally, they say, for example, when you talk about the heart, some of the latest technologies are so-called as physician-nears, which is the combination of physicians and engineers. They recommend that you should somehow maintain even the circulation. But even otherwise, you should actually maintain some fair level of temperature gradient, then sanitation system in order to protect the container surfaces, then constant transportation effectiveness, then safe nesting place for organ, then real-time monitoring, what is happening. So all these things have to be considered, which means even that enclosure design itself has a lot of critical ingredients. So we did study some of the things that they say that metabolism at 48 degrees slowed down but still is persistent. Then below 2 degrees centigrade, if it goes, then it increases the risk of cold injury. So it does some protein mutations, etc. So that is also a problem. About 12 degrees centigrade is another type of problem where the metabolic demand for oxygen leads to some irreversible hypoxic injury, and it can impede the organ. So there is a need to maintain the temperature between 4 to 8 degrees centigrade. So we need to design such a chamber where we can maintain the temperature and monitor in real time. So which means when the eVTOL is going, let us say for 100 or 200 kilometers, then we need to really look at how to have a continuous monitoring system. So this is the overview of the box. Of course, this we have, I'm sorry, I have not quoted the source of this paper, but this is from a paper we have taken some of these dimensions, as you can see on the right side. So maximum weight of this box would be something like about 20 kgs, including the organ, be it be liver or heart generally. So this means that your eVTOL, the payload should be about 20 kg plus maybe other things like maybe a camera, etc. So about 25 kg payload, and your vibrations from the vehicle should not go to this. Therefore, you should have a good vibration isolating system also, because we don't want the organ to be disturbed in any case. And range should also be reasonably high to reach inaccessible areas. So design an aerial vehicle that is able to carry the organs in a special box or a customized box, and this should contain all the equipment to keep the organ in live condition. And depending upon the organs, when we say approximately 4 hours, it not necessarily means for all organs, for all types. It could be 1 hour, half an hour, but depends upon from where to where, etc. And what kind of technology do you use to preserve their working? As I said, you can have a live circulating system where you somehow keep the circulation in the heart quite lively. So such things are also possible, but depending upon that, the durations can vary. So ultimately, you should have a VTOL platform which can, take care of the constraints of takeoff and landing. You can do it on a hospital rooftop, and of course, necessary propulsion systems to provide long range and endurance. So that is how we came to these requirements. The payload requirements, like organ transport box is about 20 kg, and you need to have a live video system and maybe some lidar and sensors to take care of some obstacle avoidance, etc. A total payload of about 25 kg. Then we, as a design problem, we took it as 400 kilometers. Then service ceiling of about 2000 meters, considering the northeast conditions. Then cruise speed of about 100 kilometers per hour, and propulsion should be hybrid, because this kind of a range and endurance you cannot just get by batteries. It may be difficult. Therefore, we thought we'll have an IC engine, and we are also working on how to reduce or minimize the vibrations that come from the IC engine. And of course, since these organs are very, very sensitive, they matter a lot, and therefore safety systems have to be in place. That also we've been working on. We have done some testing of parachute using a hexacopter. We have tested, but on this also we intend to use this para drop kind of thing. Plus, of course, precision landing analytics will be built in, so that you can perch onto a designated platform without any great impact. So we started with some benchmark analysis for this kind of payload and this kind of category of VTOL. We just studied, we picked up various, of course, representatively we have put 4 different configurations that are considered. And generally, the right side table gives us the specification summary. What is the wingspan approximately, ranging from about 5 to 6 meter, length about 3 to 3.5 meter, cruise speed of about 100 kmph, and MTOW of about 110 to 125, and then similarly flight time. So this is our starting point. Then the design methodology. So first we went with the design requirements, then what should be the mission profile and analysis, then configuration selection, then we went with the conceptual design, initial weight estimation considering the constraint analysis, then component sizing, and we did the low fidelity aerodynamics and did some performance calculations. Then we did the detailed design and high fidelity aerodynamics, and then stability and control analysis, structural analysis, and final weight estimation. And of course, we all know that this is a iterative process. And then once we are now still doing this process, the design is nearly reaching completion. Once we converge, then we create a prototype, and then we take to manufacturing stage. So looking at this conceptual design, we have the design requirements based on the mission performance, stability, etc. Then primary VTOL configuration layout, we have to do this. Then in this, we have to select the multi-rotor frame, the class and type, the wing configuration, tail configuration, what type of propulsion you need, then generate the views, then optimize the configuration. Then once you do this iterative process, you get to the optimized configuration. So when we did that, this is what we get. So this, as you can see, this is sort of a X configuration, when you talk of the four rotors for vertical takeoff and lift, and you have a pusher configuration, and yeah, for this lift and cruise. Then you have used the X frame and this coaxial eight, because we know that by using this coaxial we will lose easily about 25% of the performance, but yet we want to save, because most of the time it's a cruise vehicle. We want to save on the drags, the additional rotors, etc. Therefore, we stuck to this configuration. And if you look at the rotors and of course high wing sailplane kind of thing for better gliding abilities, we have used, and IC engine pusher we have used, so that there is no uh, interference from the main propeller onto any of these things. So with this, and also you can see there is a staggered arrangement in the front two propellers vis-a-vis to the hind propellers. We did some studies to decide upon how much of stagger. There's a vertical differential that we need to provide for these things. We choose standard VTOL tail design. Of course, this VTOL, especially in these kind of VTOLs, will help us to provide directional stability better. We have done a lot of parametric studies also on this VTOL angle, etc. So this is the mission profile. VTOL takeoff, then there's transition, then there is climb, cruise, descent, and land. Based on this mission profile, you can see the numbers, what are the kind of speeds that we have given. And well, most of this cruise is handled by this gasoline engine or IC engine. The preliminary design, I'll not spend much detail because we have a very learned audience. If it is too preliminary, please excuse. Fundamentally, what we did the preliminary design phase, in which aircraft performance design requirements we did estimate the MTO, then maximum takeoff weight, determine the wing area, engine thrust, power. So we did all that. Then maximum takeoff weight estimation is done considering all the structural weight, subsystems, avionics. Some of these things, of course, are taken from the design handbook as a empirical calculations. So that's how we arrived at the size. So you can look at this scatter plot of MTOW against payload of various other configurations, and that you see that regression line. So we also fit into this. So that's how we also choose the maximum takeoff weight to be around 120 kgs, and you can see other values of rate of climb and descent in the table. So this is how we started. Then battery weight estimation, we had to get to this, and this is for takeoff, hover, transition, and transition from VTOL to forward, and then some forward to VTOL, then VTOL landing. So these are computed, and you get the mass of the battery to be approximately about 13 kgs. Then the fuel weight estimation, use the standard textbook algorithms or the approach, and then we have computed what is the fuel weight estimation. Mass will come to about 8.5 kgs. The structural mass estimation we have done using standard design books. We have taken reference of Gundlach, which of course Gundlach says about less than 20%, but that's for a fixed wing. But here we have other accessories like rotor mounts, etc. So we have taken it to be about 30% of MTO. So we get the structural mass, then the subsystem mass, then avionics mass. These are all standard things that we have taken. When it comes to this propulsion system, so VTOL propulsion system is the motors, which is T motor U15. 2 is the designated one, about 1.74 kg, and you have electronic speed controller and matching propellers as given here. So we have the weight. Then for forward propulsion, we have because we need about thrust weight during cruise about 0.5. We have chosen DLA 232 cc, weighing about 7.27 kg. And you can see that then propulsion system mass will sum up to about 28 kgs approximately. The total weight, now we compute from what all we have done, and MTOW will be about 126 kgs, and whatever we started with our initial assumption, it matches. So this is the constraint analysis to find out the feasible region of operation. As you can see, the power loading is about 44 newtons, and the wing loading is about approximately 300 newton per meter square. On right side, you also see some of the assumptions that, and standard assumptions that we have made. So this is the matching plot. So we arrive at the component sizing. Cruise velocity of about 100 kilometer per hour, aspect ratio of 8, fuselage length to span ratio 0.6, fineness ratio about 4.5, and wing taper ratio also we have taken to be about 0.4. So this is overall how the wing looks. So there is a sweep, because the basic calculations are also given. Sweep is very slight, about 2 degrees, taper ratio of about 0.4. And the fuselage, yes, from the literature, fuselage is 40 to 60% of the wingspan. So we started from there, and the fineness ratio, as we shown in the last table, we arrive at fuselage length of about 3.46 meter and diameter about 0.77 meters. So this is the, for the tail, we use the standard techniques as we all understand, and we get the tail arm, tail area, tail span as indicated in this table. Then the wing aerofoil selection, we did study, as any designer would do, variety of aerofoils, and we converged to NACA 4412 because that satisfied all the requirement that we had. And it's also the stall quality, it is docile, it is not sharp. So that was another added advantage. So we thought we will go with that aerofoil. And the tail aerofoil selection, and we have kept it fairly simple. NACA 0010. And you can see the parameters in the table. And when it comes to the uh, boom configuration, whether to put it in plane or staggered, we thought in plane, especially when we are cruising, the front rotor wake may interfere with the rear rotors. So we did some low fidelity analysis to look at what kind of stagger to be given, or if the stagger is necessary at all or not. The flow conditions are given there, and we did a low fidelity analysis. As you can see in the in-plane, when it takes the left-hand side picture, there's strong interference between the front and the rear rotors. Whereas if you see here for the stagger, even for an angle of attack of about 5 degrees, 10 degrees, we have seen that there is no appreciable interference. So we thought it is good to have a staggered boom locations. Then this is the comparison with the X frame, plane, staggered, and the H frame. H frame we did not go because fixing these booms to the fuselage will create more additional loading on the wing itself. When fixing it to the wing, the H configuration, that can lead to other problems. So we did not pursue that, but you can see that the CD, the drag polar, reasonably okay when you take this X frame staggered. So the performance characteristics are given here, the atmospheric values, what assumptions we have made, and the cruise, climb, and turn. The parameters are given here. Then we went with the stability analysis, both longitudinal and other three things. So we have a tail diagonal angle of 36 degrees and static margin 9.59. Then this is for directional and lateral stability. Then we also did for the tail the parametric studies by varying the angle of attacks and then the moment coefficients. You can see that tail diagonal angles variation. So that also we did. So the initial tail design did not provide acceptable stability requirements. So we had to do this, and we fixed optimal diagonal angle. So some more on the parametric studies. I will not go into the details of these things. We have done all these studies to arrive at the optimal configuration for the tail. Then we recomputed all the stability analysis and compared to the previous graphs when the tail was not optimized, this we were able to achieve better stability characteristics in all the three parameters. So this is the overall result from the static stability and sizing parameters. So this sums up this overview. Now coming to the propulsion system for the vertical flight, we chose T motor, and total thrust is about 216 kg. So some of the other parameters are there in the table. Then when it comes to the forward flight, we have the IC, that is the SP275TS ROS engine. It's a two-cylinder gas engine. It is 275 cc engine. We did use that, and we are aware that there could be some issues with the vibrations. So we also have designed a vibration isolator. And this isolator, of course, the weight is not much. It is about no, it's about less than a kg. I know that. I think.
SD card to झालेलं का?
So this isolator, now we have done some studies. I don't have those results here, but it minimizes the vibrations to a great extent. So this is essential for the type of problem we are trying to solve. So this is initial VTOL. This has nothing to do with what I have discussed now, but an initial thing just to test our control, etc. we have done. This is our AAC airfield. Now the airfield we have almost lost. The airfield almost gone. So that's the transition. Well, one of the advantage with this sort of vehicles is that the control things are quite easy and straightforward compared to the yes. So with that, I think I will conclude the first part of my talk on what kind of work we are doing in VTOL. And if the chair permits, I will go into drone analytics. Or if there are any questions on this, we can also do that.
Sir, we can take the questions at the end, I guess.
Okay, so I will
continue. I mean, we have 10 more minutes usually.
Okay, yeah. So we also work on drone analytics. Basically, the flying drone for whatever purpose is one thing, but drone data deciphering is very, very crucial. This is where we use a lot of these AI related algorithms. So what we have done is, one is on the non-availability of GPS, or in case of agricultural fields, when you have a lot of obstacles, how do you really maneuver? Here you see this one of the thing. This is autonomous. No pilot is controlling. It's a monocular camera. We used texture-based learning algorithm. This is the woods in the IAC, and it simply goes through that. But the problem with this texture-based algorithm is that when there are horizontal, let us say, branches of a tree, then it may not really do well. That's where we use the optical flow-based algorithms. So they are more efficient, very lightweight algorithm, because the Arduino board is able to do all these things. And then there is pathways. When you have pathways, for example, there is a military convoy which want to go ahead in a pathway. We don't know what is ahead. Therefore, is it possible to create algorithm for path following? So we did that path following algorithm, and this is what it is. It's a path following algorithm. You can see the IAC road here. The drone centers itself to the road and goes. On the right insect is shown how the computations are happening inside, how it is detecting the road edges, and how the drone is centering itself to the road and goes. So one can know where the road is going and what is ahead. So many things can be done. Then we used the last thing, it is actually the as of to the satellite remote sensing, which is high altitude remote sensing. These days, this low altitude remote sensing is becoming a buzzword. We have used a lot of such algorithms. especially for paddy, health and yield. There is some background noise. Someone is, I think, he has to mute. Kindly mute your system. Okay, so for agricultural, we have used the multispectral camera, which has 5 channels, and we have done this study in Kerala for more than 2,000 acres of paddy. All in Palakkad area, you do the waypoint navigation, everything, and do the flight plan and go there and fly, get the data. These are the 5 bands. You get RGB and NIR and red edge, and through that you can compute various indices. And one of the things that we did was to compute NDVI indices, and we recognized that NDVI in one place was less than 0.5, which means it's a diseased crop, and it was verified through ground truth to be so. And then we have done on the yield prediction of tomatoes. We used several techniques. First, we started with, well, this is the image taken from a drone, and then we need to estimate the yield. Initially, we used self-organizing feature maps. Later, we developed into the object detection techniques of ML. And now you see the tomato can be picked up as an object. So number of boxes is equal to number of tomatoes, and the size of the box is proportional to the size of the tomato. And you also have the RGB information, which means you can grade the tomato, you can calculate the yield of the tomato. And most of us are familiar, especially in our region, tomato prices, they oscillate very violently. It can vary from 50 paisa to kg to 80 rupees per kg, because supply demand is not well understood. So we thought this could help. And of course, the tree crown. If you want to extract what is the nature of the tree, what is the species, that can easily be done. We have used all type of, this is IISc tree cover. Then we have created our own mango network with huge database, where just like tomato, we can pick up all the mangoes. You can see there are boxes around the mango in this picture. Then we were the pioneers, myself and Professor K.P. Reddy, to use the UAVs for afforestation. Conventional method we all know, so we actually did our first experiments some, I think 7-8 years back in Gauri Bidnur area, and yeah, we created one aircraft, and especially to carry the seeds. It can carry about 10 kg of seeds with appropriate dropping mechanism. You can also carry different varieties of seeds and drop them, whatever seed, wherever you want. The whole idea is that you can use the waypoint navigation and then fly in the same area, maybe once in 3 months or 6 months, so that you can know what is the impact of seed dropping on the local ecology. Then we have done something on the pomegranate. This is one of the recent studies we have done. So you can compute the height and the canopy diameter, and through that you can compute the yield. So this is what it is. We have compared for a place near Chitradurga, and you can find out what is the average yield, etc. Then we have done one of the important work is that detection of violence using the drone imagery. This we presented in the CPR conference, a leading conference in image processing, and it gave us a lot of publicity too. The whole idea is today any mob activities, etc., they are anywhere, huge mob is there, you can fly drones to monitor them. Drone feeds can come, but the whole point is when there is a violence activity or any sort of things like protests or chain snatching, automatically can you detect, can you flag so that in this lat long location there is problem. The whole idea. So we developed a three-step architecture using machine learning techniques. The first one is, of course, we have to detect the human. We created our own data set. You can see this is the airfield at IASC, where our lab students, they did a mock drill because we wanted to create a database of violence activity. So we did that. We created our own data set, and then first is human detection has to be done, because if in a scenario if two dogs are fighting, we should not raise an alarm. So first is human detection, then pose estimation, how the people are engaged, what kind of pose they are in. That is the architecture you can see here, quite the regression network, and this will tell what kind of pose they are there. Then the orientation between the key points of whoever is engaged in the pose, so that you can then classify, identify whether it is violent or not. And multiple violence activities can also be identified in this algorithm. You can see all multiple things you can pick up in one go, and this can be flagged. And this actually attracted the media also, and BBC interviewed us. Just I'll play it for a minute, because this is one of the small thing that I use for boosting our lab. This is my student who is now in US. Yeah. Then of course the flood is a perennial problem we have, and it is important to detect the number of people who are trapped in any situation, including captives, for example, because we have seen that in many places, when the rescue teams went, recently it happened, they said the people decided, they took a boat which can carry 8 people, and when they went there, there were 80 people. So there was a lot of commotion because who has to get in, etc. So they could not plan properly. So we thought, okay, we can use an algorithm so that when you get the, as and when you get the imagery, you also know, identify how many people are there, how many cattle are there, etc. So we have come out with our own network to do all these things. And you see, it picks up whether they are on the rooftop or caught up in, or if there is some animal, a human, everything can be picked up. So the rescuers can plan their operations better. Another important thing that we have done is about the radiation monitoring. This is what we have done. In case any radiation mishaps take place, we know that it is all dangerous. Human intervention is impossible. So we thought of using a Giger-Muller counter where you can measure the radiation levels. So we designed a special vehicle, because you know that Giger-Muller counter is a very sensitive, a glass tube. So impact matters a lot. Although design considerations were done very sliding, because it had to be, it had to cater to all that. So we did that. When we wanted to test, we had difficulty, because where do you get that kind of radiations? If you lab level cobalt, etc., the radiation level is limited to about 1 feet. But we want to fly quite high, at least about 300, 400 feet. So that was the problem. Then we found out that the Chavara coast in Kerala has natural radiation levels 12 times higher than Bangalore. So that's where we started our testing. So here is a small clip which will tell you, which will capture the work we have done with regard to radiation monitoring. So these are some of the historical things that went wrong. This should be over in another couple of minutes, so bear with me. Yes. So we went to Chavra Coast. First, we mounted this on a quadcopter because we need to look at how the instrument itself performs. This is the sensor board. So we did some variation in the altitude, etc., just to check, to verify that we are able to get acceptable results. And you see, yes, this bottom curve, you see, is Bangalore IISc, 12 times higher is Chavra Coast. So that confirmed that things are working. Then we wanted to do the large area scanning. So there's the Bungie launch. We went with the fixed wing architecture. And all around is the sea. You can see the waypoint navigation, where all it has to fly. And then when it lands, it has to be very smooth. It does a belly landing. Yeah, so that's how we did. And you get the real-time data. You get the counts per minute and the lat-long locations. So this is the onboard GoPro video. You can see. So you can get a heat map of how the radiation can go. Yes, this is our one of the experiences. Sometimes things can go wrong. When we're doing, our team lost the communication. So this is after we recovered. The post analysis all around sea. They thought it must have dived into the sea. I'll show you the onboard video. We thought we had lost about 6 lakhs. Kerala being the land of gods, God smiled on us. So it is the onboard video. We thought it had gone into water, but look, it just hit a coconut tree and nothing happened to our aircraft or the equipment. Some savior came and he took it, and our students has to search for about 7 hours, and this was about 11 kilometers away. And that's how we actually recovered. So now we have a system which can monitor the radiation levels. Yeah, many other analytics we have done, but I thought I'll just include few basic things. So this is what we see that you have to use this on any kind of drone along with cloud and big data and AI to make it more meaningful. Jai Bharat. So I conclude. Thank you for accommodating me. Thank you very much. Namaste.
Yeah, okay. I
All
started
right.
the recording. Please go ahead.
Thank you so much, Professor Abhishek, for this invitation. It's a real pleasure and an honor to be amongst very high dignitaries in this forum, as well as very curious students. So my name is Omkar Halbe. So I just recently joined NAL in Bangalore. I'm posted in the Flight Mechanics and Control Division in the Controls and Handling Qualities Group. So when I was thinking about what could be a topic, rather than having something very academic, I thought of sharing some experience which I have gained in the past decade which might be useful for both young students as well as startups or any industry people to look at how we have gone about developing and certifying safety critical systems. And especially for the autonomous VTOL, what could be the challenges in design safety and certification. So here is the outline. So I'll firstly talk about what is the objectives of autonomy in general for different kinds of aircraft. Then we look at how conventionally we have gone about developing, done the development and safety assessment for aircraft and systems. We look at how AI ML applications are, slowly entering into the manned aviation, manned VTOL. And if time permits, I'll have a case study on what could be the possible approach towards certification of a fully automated VTOL landing guidance. So none of this is going to be exhaustive. I'll have to be upfront, but I'll just try to give as much details as possible. So on the objectives of autonomy, I'll just start with a short video just to have a kind of a teaser. So this was a recently concluded autonomous taxi takeoff and landing on an A350. So what you will see is that there were some sensors mounted on the nose of the aircraft, which were the function was to detect the runway center line and the edges of the runways, and that was then directly guiding the flight control computer. So this is what is the so-called active hands-on, where the pilot is, attentive hands-off, where the pilot is attentive and can take control at any point. But at this point, the pilot is actually completely monitoring the aircraft. The another one is also another example that was published very recently. So this is a unpiloted Sikorsky. So this was actually flying without a pilot, but a remote pilot. And it was claimed that it performed all kinds of maneuvers that are encountered in usual missions. So this is a remote station that is being piloted, and as you see, there is a takeoff which is without the pilot, and some additional features that were implemented. So of course there is these are efforts that have been going on for a long time, but only now we have been seeing, and yet it is not actually something that is unpiloted autonomous self-driving. These are not yet in industry, I mean, not available to users. So it's important to know what do we mean by autonomy. So here a lot of buzzwords like autonomous, self-driving, unmanned, but these are actually misnomers because everybody may have a different understanding. Autonomous for me might mean a different things. Essentially, what is automation is that it is the use of electronics or mechanical devices, so essentially machines, to replace human labor. And that has been going on for time, at least since the advent of machines for agriculture in the old ages. Now we are only seeing that the machine is trying to do a lot more things. So what is the recommended taxonomy this is coming from the automotive industry, is to use the word automation system, and to speak about the level of automation. So how far is an automation system controlling the vehicle? So here is a brief timeline of how things have evolved over the decades if we speak about aviation. So there have been in the 1930s, the invention of the gyroscope and the gyrostabilizer radio beacons that were providing direction information to the aircraft. Then in the 1940s, 40s, during the World War, there were the first autopilots developed. Coming on into 1970s, which was the dawn of the digital computing. So a lot of the data was then done by computers, digital computers. So this was the time of air data computers, flight directors, area navigation to provide navigation features. And today we have the so-called glass cockpits, or the so-called integrated modular avionics. So what it means is that all these instruments have been replaced by glass cockpits. So these are basically multifunction displays. The conventional controls have been replaced with side sticks. So this is the most recent Bell 525, which is the fly-by-wire helicopter. It's a medium heavy helicopter. And it is, as I understand, was close to certification until last year. Right, so again, looking at how the cockpit has evolved, this is the first Airbus aircraft that had all the dials and the yoke, the conventional primary controls, and the latest one, A350, is completely changed. So the first thing that is noticed is that the centers, the primary flight controls has been now in a side stick, which is a fly-by-wire system. Then the dials have been replaced with multifunction cockpits. And then there is this small piece here, glass, which is the head-up display that provides pilots display on the head-up screen rather than having to look down. And that's really useful when landing and looking out at the same time. In conventional VTOLs, there is also already high level of automation existing. That is also enabled by the so-called avionics systems. Avionics stands for aviation electronics. It's a combination of these words. And a lot of the missions that are performed today are supported by automatic flight controls, guidance, and navigation. So here are a few missions that are performed worldwide by commercial helicopters. Some of the phases, as you've seen here, are highly automated. So that means that some approach procedures, for example, landing on an airport or runway, the pilot can already have a 3D guidance to a certain height above ground. The last leg is flown manually, of course, with support of the autopilot. Likewise, other missions like landing on a hospital, picking up accident victims, landing on a moving ship, nowadays servicing offshore oil platforms and wind farms. So this already has a high level of automation. And when we speak about automation in VTOL, again, it's useful to speak in terms of what is the level of automation. So starting from a level 0, where no automation exists. So the pilot is basically doing the entire flying. Level 1, which speaks about task by task delegation, but this is limited to very small tasks, and that could be simply to hold heading, to hold height, things like this. The level 2 is partial automation, which is multiple tasks can be automated. So meaning multiple axes of the aircraft can be automated. Typically in VTOL we speak about 4-axis autopilot, which is controlling all the 4 control channels. And level 3 is the highly automated. So these are automating a complete segment of phase of the flight. So that could be a climb phase, en route phase, approach phase, and that's where beyond this point starts the higher tasks are being done by the machine itself. So level 4 onwards, it's fully automated, and level 5 is autonomous, where and at level 5, all the tasks are basically being done by the machine itself. So it is important to also consider when we speak about level of automation, in which flight phase are we talking about? So these are different considerations that usually go into the brainstorming whenever an automation function has to be developed and certified. So one is the flight phase. So in which flight phase is the automation applicable? Then what tasks are being automated, whether it's the basic piloting tasks or navigation, communication, or any other mission related tasks. Then what is the system states? Is the automation applicable only when all systems are normal, or whether it can also work if some systems are degraded, or whether some systems have failed, and then despite that, can the system still provide the automation without requiring human intervention? Likewise, environment, because environment affects the conduct of light. So whether day, night, rain, fog, snow, dust, gusts, what is the wind conditions? These are all considerations. Whether it's flown only in controlled airspace where ATC is providing coverage, or whether it can fly in any uncontrolled airspace where there will be no other means of communication, whether it will be able to fly over populated areas where the risk of injury to third parties is high. Do we have existing regulations? So the new functions, do they fit into the existing framework, or do new rules have to be generated? Again, legal aspects in case of incidents or accidents, who is liable? Because obviously machines cannot be held liable. So somebody has to take responsibility by law. So it is safe to say that most conventional contemporary helicopters, so even I would say the conventional single main rotor design, can reach up to level 3. So certain flight phases can be fully automated. What is the challenge now is to reach the level 5, where that is the dream of most companies, as you see from the conventional ones to the drones, to the optionally piloted electric VTOLs. Everybody wants to have something that the machine does everything, but the challenge lies in ensuring that the design is safe and people can trust that. So that brings me to what is the requirements, or what is the globally speaking. There are these 4 categories of VTOLs, including the eVTOLs, which require some kind of automation. So the first is the conventional, commercial and military helicopters, which typically are used for passenger or goods transportation. So the HALs, helicopters, the Sikorsky's one, which is landing on a ship deck, others which are used to ferry people. In this case, it's the maintenance. So can such missions can be automated? That's the first question in this. Then using the conventional helicopters to make them unpiloted. So recall the video that we have just seen. And there are other platforms where 2-seater helicopters are being converted into optionally piloted. The third is a large category of small and commercial small rotorcraft, which are for commercial and military, and we have seen Professor Omkar's presentation, where he has shown a wide variety of examples of this class of helicopters. Right, and one I've taken a picture from Professor Abhishek's own initiative. We here at NAL have also an octocopter. And the last category is these all unconventional electrically powered configurations, which can range from tilt wings to tilt rotors to fixed quad rotors, a large diversity of configurations. So of course, these are the requirements. Everybody wants to increase the level of automation, that is clear. Now the question is, how do we go about that and still make sure that the design is certifiable by, because finally, if somebody has to operate this commercially, any of this, or somebody has to use it for a military operation, then there has to be some level of safety and reliability associated with each of these platforms. So typically it's the civil aviation safety agencies responsible for commercial, and the CEMILAC, or the military airworthiness agencies, for the military aircraft. And it is imperative to pass through these agencies in order to get approvals for commercial usage or military usage. So we look at how the conventional processes have been done. Conventionally, how things have been developed, assessed for safety, and gone about developing the systems. And because whatever are the new rules, they will be built upon what has been the experience of decades of level up to level 3 automation, right? So we have these broad set of documents. I mean, there are a lot many, but I have just condensed this into a few 5 to 6 ones, which are the main ones. The first one is the certification specifications. The 27 number, these are the numbering used more or less globally. So 27, CS27 is for the normal category rotorcraft, 29 is for transport category, so larger than 5.5 tons. And then the very light rotorcraft. And then there are some new rules for the unmanned aircraft. Then there are these two documents from SAE, SAE Aerospace Recommended Practice, number 4754 and 4761. First is for aircraft system development. So this concerns the processes applicable or the processes, recommended processes to be followed for design assurance or development assurance of aircraft and its systems. And the second one is to assess safety, of the design itself. Then once the system and aircraft level documents are there, there are also guidelines and standards for how to develop software and how to develop hardware. So these two documents are the industry standards for safety critical software and electronic hardware. So these are most commonly referred to in many discussions, and all the applicable chapters are most commonly referred to. So why do we need all this? It's a very process heavy industry. I have to be very frank, working in the aviation industry is a very small part of design and a whole big set of processes and documentation. But the reason to do this is because this industry relies on trust. When we take a flight of any commercial airline, we don't think about whether we'll reach home safely or not. It's a no-brainer. And the reason that this is a no-brainer is because all these processes have gone in, and we have reached a level of that faults have been reduced to an acceptable level where even if a fault occurs, the airline is prepared to have mitigation measures. And it's because it's required also by most airworthiness agencies. So this is imperative. How does it go about? So it considers the overall operating environment of the aircraft, in which environment it occurs. You might recall that in the previous slides, we have seen different considerations like flight phase, environments, which are the tasks that are being automated. So these are considering the overall environment. And anybody that is intending to develop commercial or military VTOL, which requires some level of assurance to the end user or to the customer, these guidelines are most likely evoked. These are also used because it is especially applicable for systems whose failures may have severe or catastrophic effects on aircraft crew or passengers. So meaning that if something fails, then a human life is at stake. So we'll quickly look at what are these processes without getting into too much technical details or without too much jargon. But this is a high-level diagram which shows that in the middle you have this ARP 4754, which I just mentioned. This is showing the process flow. So this is the process for development itself. Then there is a process 4761 for safety assessment. And then based on these documents, there are lower level documents for hardware and software. So these two set of processes are applicable for the overall avionics installations, which are basically all the electronics and systems, sensors, actuators, everything that goes into the aircraft. And then as we move at equipment and component level, we encounter one is this the so-called integrated module avionics. So meaning that many functions are hosted on a single hardware. Right, and then at equipment level, there is the guidelines for standards for the hardware design itself. When we zoom into one of these processes, so I'll just try to walk you through what are the different considerations when we do systems engineering. Here, this is the flow chart of the process. So there are some activities to be done in progress. And there are some integral processes. So first we start with the concept, we do the function development, and then we allocate functions to systems. And I'll go through through these blocks one by one. And then there are some integral processes. So these are integral to each of these blocks. Then there is the overall planning. So planning would include, management requirements management plan, certification plan, safety assessment plan, systems engineering plan. So these are documents which are established, which are kind of giving an overview of how these activities have to perform, the life cycle of all these activities. And it all ends with documenting each of these activities done throughout this process. So example of the concept, it's typically operational needs. Who are our customers? What are their needs? How much range do they want? What is the payload, or how many passengers do they want to fly? How high does it have to fly? In which environment do they want to operate? Then based on that, what is the business case? What's the price would be, the cost model? What are the services that will be provided by this after the aircraft is certified? So these are all the activities done in the concept phase. And of course, all the aeromechanic configurations, doing the benchmarking of different configurations, as was cleverly shown by Professor Omkar just before. So all the pre-design and conceptual level activities at this stage. Once we are sure what configuration, what is the business case, and then the project has been sanctioned, we would go on to develop the high-level aircraft functions. Typically, if we do speak about VTOL, it's going to be providing thrust. If it's a single main rotor, then provide anti-torque. And if it's about the piloting itself, then it's to determine position and orientation. So these are the high-level aircraft functions. So that's the first level of breakdown for the aircraft. So as you see, it's not an exhaustive list. I have just stated things that are quite obvious here. And then one would also break down these functions into sub-functions. So for example, if we speak about controlling flight path, so obviously we want to control an aircraft's flight path, and that can be done either manually, or it could be done through automatic control. So provide automatic and manual control. If it's through our automatic control, then we would have different kinds of automatic controls. or functions would be stability and control augmentation. It could be trajectory control, and so on. So these are just at function level. These are not yet talking about what systems, what sensors. We are just seeing what is the function that this aircraft has to fulfill. That's all at this stage. So once we are reasonably sure what functions have to be fulfilled, and we break them down at a certain level, and then we define function requirements, then we can actually start to allocate these functions to systems. So usually what would be done is, we know that a position and orientation is provided typically by a positioning system or an attitude and heading reference system. Thrust is usually, if it's a single main rotor, it's the main rotor system, the main gearbox, the power plant, and so on. So these are all systems that will be installed on the aircraft. And so here we are assigning that this system is performing that function, or that system is providing that function. So that's the level of, that's the kind of allocation we are talking about. So once that is done, we can then start to interconnect these systems, and we can see how these systems operate along with each other. So what are the interfaces between these systems? What data is exchanged? This system architecture could be either at system level, so meaning physical equipments, or it could be at function level, where we say that these functions are exchanging some kind of logical data. But here you see it's a physical architecture, because we are showing physical equipments or boxes, and they are connected by physical wires. So once that is done, we can also then go down at small equipment level, and we'll try to allocate requirements to items. So here items are hardware items or software items. Here an example is taken for the aircraft management computer. So this is the central computer of an aircraft, which provides the flight control, which provides guidance, does sensor fusion, can do engine management, vehicle management. Here it might be a dual computer for redundancy purposes. So you see there is a processing board 1, processing board 2. So these are all requirements of the computer, and then the process says that we have to allocate requirements to the items. So meaning there is a software item which is hosted on a real-time operating system, and that is doing the function requirements allocated to this is the autopilot. Okay, so of course, there are a lot of other components in this computer, and each one will have their own requirements. So as you see, these are requirements broken down to smaller and smaller levels. And there is a constant level of kind of a traceability from high level to lower level. Okay. And finally, when everybody is satisfied that the requirements are correct, they are concise, they are all well documented, they are traced, then we start to implement these functions, and each single item would be then developed. Of course, it's not everything done by one, but it's a whole ecosystem doing all that. And everything has to be then documented. How is it designed? The design has to be documented, the whole tests and everything. This doesn't speak of the test itself, but the whole process has to be documented. So that's about a little bit about the design itself. But of course, all this has to consider the safety aspects. So safety is an integral part of the development process. And a quick motivation of why it is essential is because there are consequences. And one quite good statement is from Wilbur Wright in a letter to his father, says that what he has learned from flying is that carelessness and overconfidence are usually far more dangerous than accepted risks, right? So that means that a designer, of course, knows best his design, but that doesn't mean that the designer must be overconfident. This confidence must be backed by evidences. So that's the whole point of it. And then there has to be a risk management. The risks have to be mitigated to an acceptable level. And that is the way to actually design the aircraft and its systems. And everybody knows the consequences of unsafe events. It's that human lives are at stake. Third parties, people on ground might be affected. Their lives are at stake. There is a huge loss of reputation. So you might have seen some incidents in the past years which have led to such a loss of reputation. Loss of public and customer trust. So if nobody trusts the designer, then of course nobody is willing to buy it, right? There are also financial implications because people might file claims or lawsuits. Again, the point is that no system is ever 100% safe. It is always a question of when it fails and how it will fail. And this is what is the whole point. We have to understand, when does a system fail, how will it fail, and what will be the effects of this failure on aircraft and its occupants. And that is the whole objective of this assessment process. And that will tell us that aircraft and its systems perform their intended functions within a defined domain and for the specified limit. There is always a life limit, and there is a defined domain. And as long as the operation is within this domain, it has to perform its intended function, and that's only then will the crew trust the systems, and only then the crew can be trained to handle anything that goes beyond this intended function. This is a very famous model that is always shown in many of the safety discussions, which is the so-called Swiss cheese model, because the Swiss cheese has sort of holes. And what it says is that hazards are always there. A gust of wind is a hazard to an aircraft. Bad weather is a hazard. Wet runway, rain and a runway which is wet is a hazard for your aircraft. But there are successive mechanisms and defenses and barriers built in the design itself, that everything is mitigated. And there is possibly one that might still lead in hazard. Follow a hazard can lead to a loss. That's the whole point, that the intention is to have mechanisms which can avoid losses. So that brings us to the function hazard assessment, because here we speak about hazards, all the hazards that can be present that can lead to a loss. So that has to be then assessed, and that's the so-called function hazard assessment. It concerns only aircraft and its systems. It doesn't concern human factors or operations, so meaning it doesn't state that the pilot can abuse or misuse the system, but it only says that within its design, how is it designed to be safe. Formally said, it is to identify all possible failure conditions and to classify the effects on aircraft and its occupants. So typical failure conditions of any function are, for example, the function is lost and it is not even announced to the pilot that the function is lost. A function could be, signaled, so meaning the pilot sees that a function is lost. A function has, there is an undetected erroneous operation, so meaning that the pilot doesn't know that it is erroneous. For example, a sensor giving a wrong data. Untimely operation. So for example, a landing gear that is programmed to deploy at a certain phase doesn't deploy on time, and it either deploys very early, which could lead to aerodynamic loads, or it is deployed too late, which could cause a hard landing. Inadvertent operation, so meaning a function that is not required to be in operation is actually operating. And then what are the effects of all of these conditions, whether it's going to have a catastrophic effect, hazardous effect, major, minor, or no safety effect. Catastrophic is typically loss of human lives, damage the complete aircraft hull. Hazardous means that there is a serious risk of loss of life, but possibly that could be mitigated. Major means there is a high workload for the pilot, but there won't likely be any loss of life. Minor means there is a very minor increase in workload, and no safety effect means none of this. This failure has no safety effect on the aircraft. Once this function hazard assessment is done, there is the so-called system safety assessment based on the architecture that we've seen in one of these slides. So system architecture. Each system has its reliability, safety and reliability data. Then there are all sorts of assessments done to prove that this architecture itself doesn't lead to a catastrophic event. That is applicable for all software items, hardware items, all systems in the architecture. So example of an automatic flight control function. On one axis, you have the failure conditions, which are all possible conditions how a function might fail. The other axis is all the flight phases. So you have different phases of flight. The third axis is in the conditions in which this is operating. So whether it is day, night, whether it is visual flying, the pilot is flying with eyes out, or the pilot is relying on the instruments. So each of this failure condition is then assessed for each flight phase and each condition. And then this is a classification of whether it is catastrophic or whether it is hazardous. So for example, if a flight control function does an erroneous operation, which is not even shown to the pilot, and this is when the pilot is relying on the instruments, then it is a high likelihood that is going to be a crash. On the other hand, if there is a loss of function, meaning that it is announced to the pilot that the FCC has failed, it is at a relatively high altitude, and it is during day, meaning the pilot still can look out and fly. In that case, possibly the hazard could be less. That is why it could be classified into a hazardous condition. So this is a very critical, assessment, which, if not done right, could lead to a lot of disastrous consequences. And if it is overdone, then it might be an over-engineered aircraft. Because if everything is classified as catastrophic, then obviously an aircraft can never be built. So these are the classifications. And of course, in this case, the worst case is the catastrophic. So that is why usually flight control functions are having quality. So these are typical tables that are worked out. So this is again given in the guidelines of how this whole hazard assessment process has to be done. Again, taking an example of an aircraft deceleration function. So here its deceleration function is essentially provided by the spoilers on the wings, by the braking mechanism on the wheels. So these are different systems which are contributing to this function. And this is a a hazard, which is a wet runway, right? So this represents a hazard. So we have the function. We define that there is a loss of deceleration capability. Then what are the different subcases? If it's an unannounced loss, if it's an announced loss, and then what is the effect on the crew and occupants? And accordingly, there is a classification. And then if the classification turns out that the worst case is catastrophic, then obviously the function has to be developed to the highest level of assurance. This is a, quantitatively and qualitatively, depending on the severity of any function, one needs to take into account the inverse relationship between the severity of a condition and how often it may occur. Again, this is given, this is imposed by most certification agencies, where they say that any catastrophic condition must be extremely improbable. So that means in quantitative terms, for large commercial aircraft, the manufacturer has to demonstrate that this condition will not occur more than 1 in 1 billion flight hours. So 10 to the -9 is 1 billion. So that means practically during the whole life, no catastrophic condition may occur. So that's the whole idea, that this systematic assessment provides guidelines on how the assessment has to be done, how the severity has to be assessed, what are the applicable probabilities for each of the functions, and accordingly, through different levels of assessment, these probabilities have to be proven through analysis, through testing, or through experience. A lot of different means of compliances are available, but these have to be shown through evidence. Another thing is to notice that these probabilities might change for different levels of aircraft, because here, when we are speaking about a commercial aircraft that's usually carrying 150 or more passengers, the risk is much high. But if it's for UAVs or light aircraft, these probabilities are usually much lower. So that all depends on what is the risk of catastrophic effects. Okay, so that brings us to each function having a development assurance level. So each function, based on its classification of what is the effect of its failure, has to be classified. And then it has to be developed according to the process, such that it fulfills those probabilities, the qualitative and quantitative criteria. So development assurance level is then allocated to each function. For the functions, it's a function DAL or FDAL, and for items, meaning hardware and software, it's IDAL. So for example, a catastrophic function will be allocated of FDAL A, and examples of these are for VTOL, stability augmentation, primary flight displays. So loss of these functions would then lead to catastrophic effects. Likewise, different other functions would be allocated function DAL B if it's a hazardous, major, minor, and no safety effect. And these are some examples, so typically a weather radar or an obstacle warning function, which provides information to the pilot, would be somewhere around major. A moving map, which is showing a geographic view, would be minor. And then if it's just a basic data recording or an outside camera, which is used for gathering data, loss of that function has basically no safety effect. So thumb rule is that higher the criticality, higher is the function DAL, and accordingly more development efforts are required. Accordingly, more rigorous level of design and testing is required, and consequently it leads to a higher cost. So there has to be, again, a very balance. There has to be a balance between what is the safety and what is the business behind. Some companies, if they might go further into business cases and leaving safety a bit behind, that's also not good, because safety is neglected. Some companies focusing heavily on safety, then the aircraft is going to become very expensive, and that also is not good business case, right? So there has to be a very good balance of all these. So the overall safety development safety life cycle is shown here. I will probably not go into details, but what it says is that on the left hand side, we start from the concept. There is a step-by-step top-down approach where we go from function to system to hardware, and on the right-hand side we go from lower-level hardware software up to the high-level functions. And at different steps there are different safety assessments, and these are basically all guidelines that are followed in most aviation companies. So coming to the safety related AI ML application. So now AI ML is very popular. Everybody is looking to use it, and of course in safety critical applications there is also a strong push to have AI ML applications. So some of them, I'll just give an example of some videos that I've just taken out of internet, but these are actually showing, for example, a helicopter giving landing on a helipad, and that's again using some vision-based landing guidance. Here is another example of a traffic detection. So an incoming aircraft is being detected by AI algorithms. Then you can also use this to detect ground obstacles. And then this is another video of a another attempt to use AI for carrying sling loads from one place to another, again using a full-scale helicopter. I'll just skip this in the interest of time. So essentially, AI, as is defined by the EASA, which is the Aviation Safety Agency in Europe, is to have artificial intelligence. Artificial intelligence is this so-called technology that tries to emulate human performance through model or data-driven approaches. Subfunction of that is machine learning, which provides algorithms and that uses data-driven algorithms essentially. Deep learning is again a subset of those machine learning, which are using several layers of neural networks. So these are three levels of AI that are currently being discussed. Level one is providing assistance to the human, and the human is still in charge of taking decisions. So example would be that this kind of information is provided to the pilot, that there is an obstacle, but the pilot would be responsible to maneuver and take the decision to fly or not fly, and if to fly, how to fly. Okay, so level two is where there is a collaboration. So some tasks could be done by the AI, some tasks could be done by the human. Level three is a more autonomous machine where the AI-based function can take all the decisions, but either it could be overridable, or the last level, which is 3B, is that these decisions cannot even be overridden by the human. So some of the challenges that we face when we speak about VTOL or any function where safety is impacted is about learning assurance. So this is analogous to the development assurance of conventional systems. But in learning assurance, what is intended to be said, it is that how do we ensure that any AI ML application is free of error, that it is unbiased, it is representative of the function. So how do you make sure that this is doing as it is intended in all possible cases? And there's a question of explainability, because it doesn't, can the designer say why is the AI arriving at a certain function, at a certain output, given a certain input? So for it's possible in many cases, but in some cases where there is an adaptive learning or online learning, this is really difficult to prove at this stage. Then to mitigate safety risks especially when we speak about black box. So where, for example, an AI that has been trained on large scale data on some other function and that is being reused in aviation, and then this is a so-called black box, and how do we provide understand the risks of such a black box? And then combining all these three, there is the trustworthiness. How can confidence be gained in such an application? This is how it is envisaged that there will be some AI/ML application which is coexisting with other functions. Analogous to the development cycle, there is also the V cycle, but with a small tweak that at the bottom level, there is the model that is being trained must be verified before it is being then deployed on the overall system. So there is this additional step that is required at this lower level, where all the activities required to show that the model itself is doing as intended, it is trustworthy, must be performed before progressing to the high level design. So in conclusion, there are several opportunities for AI/ML in VTOL, which is that level 1 AI applications are certifiable. Only supervised learning methods are certifiable, meaning methods which are being trained using clear annotated input-output data, but only offline methods, meaning that where the model is frozen before it is hosted on the aircraft. What is not certifiable by today's standards are these level 2 and level 3, where the decision is being taken by the AI system or the AI application. Unsupervised learning, reinforcement learning, where the model itself would adapt, or where there is the so-called reward and punishment kind of approach to training algorithms, and also all kinds of adaptive and online learning processes. So these are also something that are currently not within the ambit of certification. So there are these opportunities, but there are still challenges if we have to really reach those level 5 level of automation. I think there's not enough time to go through the case study. So I'll just conclude here and let the chair let me know what is the next steps. I'll be willing to take questions.
Thank you so much, Dr. Omkar, for really insightful and very interesting presentation on a topic which, I mean, there is not a lot of work has actually gone on in India, especially because we are yet to develop full fly-by-wire systems for our helicopters, or even make them optionally palatable. So this is a huge area. So I'll request audience to either unmute and ask questions or type their questions in the chat box.
Could I ask a question?
Yes, sir, please.
Omkar, it is a wonderful presentation. Thank you for the presentation. What you have presented for a VTOL, I thought with some modification, we can make it applicable for a normal aircraft, conventional aircraft, but with autonomous takeoff and landing capability. Do you think we can look at in that direction?
Definitely, sir.
I thought, say, for example, today we are thinking of a regional transport aircraft which can take on land in all weather conditions. Okay.
Yes.
And if that is the case, then in bad weather also you should be able to land. I thought what you have presented, to me, it looks to be with some tweaking, we can make it applicable, and the technology is required also, we can see what we can do, and also to what extent AI and ML we can use.
Yes.
I thought, Omkar, if you can look in that direction, it would be a nice thing.
Definitely. So actually, that was actually going to be my case study of a VTOL landing in a remote terrain.
Yeah.
And I was trying to, work out what would be the process, what would be the applicable functions and systems which could enable such a function. So that was something I didn't have time, unfortunately.
But I'm talking not of a VTOL, but CTOL.
CTOL also, for sure. It's everything is possible.
Looking at the CTOL.
Yes,
okay?
yes.
That is the kind of thing, because even if it is a manned or unmanned, a CTOL landing in all weather condition, what is the kind of what you call the sensors required, what are the algorithms required, and to what extent we can use the AI ML in that direction. Okay.
Definitely.
Okay, dear. Okay.
Thank you, sir.
Thank you.
Any more questions from the audience side? I mean, I would definitely like to more about the case study that you just said. I mean, is it possible to cover it in another 5 minutes or so here? Because just give some overview of that, because that is of great interest. I mean, there is huge requirement. You are already aware of that. I mean, regarding this kind of solution. So it will be really useful to know that also.
Sure, sure. I'll try to do it in 5 minutes if that's useful for
perfect.
everybody.
Yeah.
Okay, so this was just a thought experiment. You know, it's not, I wouldn't say it's an exhaustive study. It's just, you know, what could be the possible functions, architecture, systems required. And what I've considered here is a landing guidance, the concept. So we start with the concept of operation. So for example, what we've seen is that the autopilot and the navigation system can already automate the approach to a certain height above terrain. Below that, there was going to be the obstacles, the terrain. So there's going to be all kinds of threats. And that's where this system is then, or this function is required. So where it can be installing some sensor or payload, one or multiple sensors, and it could basically survey the environment. And the requirement is then to fly autonomously, or I would say autonomous, but a high level of automation, avoiding obstacles and landing in the intended landing location. So then we have to then think about what environment do we have to consider. If it's just day, if it's night, but in mountains, of course, fog, rain, mist are very frequent. So this will be very important considerations. If it's in the Himalayas, of course, snow, gusts could be unpredictable. So these are all the environments that we have to characterize. And then we have to define the flight phases. What are the flight phases that will be applicable in this concept? Whether it's going to be just maneuvering, then decelerate to hover, vertical landing, touchdown. And likewise, we have to define for the takeoff phases. So this is the document that has to be then performed. The concept studies, as you've seen here, this is the starting point of any new function or system. Then once we have this concept, we know a little bit of what are the requirements. Then we'll start with developing the functions of the such as break down the functions. So if it's landing guidance, one function is to perceive the environment. What is the environment that the aircraft is flying in? Once the environment is perceived, whether the obstacles can be localized to the right geographic location, either in the geographic inertial frame or relative to the aircraft. Then we have to determine the own position, which is always either through GPS, or if not GPS, then other means must exist if GPS is not available. Then there has to be a function to compute the safe flight path. Then there has to be a function to execute the flight path. This function is usually then done by the autopilot, so there is not, but these four functions are the new ones. Then if it's a piloted one, either remotely piloted, then it has to be providing the means to control the this landing and to provide display and monitoring. And then these functions can be expanded. It could be further broken down into sub functions. Then usually we'll go to this allocation, where we say that the perceived environment is implemented by multiple sensors, optical system, radar sensor, LiDAR sensor. So these multi-sensors, which can also provide redundancy. Then we'll have, for localized obstacles, we have a computer which fuses all these data and then compares it with the database of satellite imagery. We could then provide position orientation, which are using standard sensors, then the navigation system that is computing the flight path, the automatic flight control system that is executing the flight path. So this is then the allocation of functions to different systems. And then we have to develop an architecture. That's the next step, where we think about how these different systems will be interconnected. What will be the logical data exchanged, and at a later stage, what are the wires, really going down at level of wires. And so that's the kind of system architecture. And then each of these blocks will have requirements that this system has to fulfill, right? And then I'm just showing you an example that I have worked previously, which is a multi-sensor installation on a helicopter, because we have done such a project in the past. So we have installed one camera here, an enhanced vision system camera. So this is already, a night vision camera and daylight camera fused together. There is a radar, and then there is a LiDAR. And then this was used for different maneuvers. And the pilot was given a display on the helmet and provided display on the top touchdowns, a head-down display. So this is obviously not complete, but this is just a starting point. And then, like we have said, that we have to assess what are the hazards. If the perceived environment, meaning the function which is looking at the environment, fails. So if a single sensor fails, but we still have other sensors operating, and we are during the maneuvering phase, we are during day, and if the crew or the remote operator is still able to confirm the integrity, then the classification could be minor. But if all sensors are failing and it's still day, and there is maybe another way that the pilot has to take manual control and land, but with a higher workload, that could be a major. Then if it is wrong sensor data itself, and nobody knows that this is wrong, then obviously there is a high risk of collision, because the true data is not known, and that could be a hazardous event. So this kind of classification has to be then done for each of the function. So it's an extensive process that has to be done. But I'm just, through this case study, I'm just trying to say that there could be such a study which is performed, which is analyzing based on the requirements and going down to the level of architecture, and then doing the development, which might be at some point certifiable. So that's the whole point of this case study. That's it.
That is really great, actually. That actually kind of very nicely covers the whole gamut of setup that is required to go about solving this problem. Okay, so that's really nice. Okay. So this is, I think, really, I would say, enlightening for me, this entire presentation. Are there any questions from the audience so far? I can imagine for students, it will be slightly difficult topic to digest, because this is, above what typically is covered in the certification is not something which is normally taught in engineering curriculum at all. Okay. So this is something which is far more relevant for industry than actually for the undergraduate students, as such. Okay. But
I think this is, in my opinion, it is very important that students are trained in this kind of approaches from an early age. Yes. Because designing something is and then retrospectively doing all the processes, it's never going to work. Right. It is always that requirements have to come first, and then the design has to follow. So it has to be always a systematic process.
Right. That's a very valid point, and this is something which we also discuss in academia. That how can we sort of upgrade our syllabus? Of course, for design, we do talk about certification and all the standards for design. But normally they barely get introduced to the autopilot and the idea of controller and basic control system. So developing an autonomous system for certification probably becomes tricky, but yes, it can definitely be taken up at the level of PhD and something like that.
So this is a systems engineering approach,
which
Omkar has presented, which is something which all we should teach in our academic institutions.
True, absolutely.
This is very vital, that they should learn how to do this job.
Yes.
This is Vijay Kumar here.
Yes, sir.
This last example that you gave, your presentation was very nice and very apt for the industry. The last one you gave, the last part, 5 minutes, it is very useful actually to the Himalayas. You have a small helicopter, or maybe a simple tool that you take the helicopter, and it has to, from Leh to, let's say, Siachen, it has to go through those valleys. On either side, you have mountains and valleys. This kind of algorithm that you talked about is very useful. So it has to be, multi-processor, different sensors, then it has to be vision based. You make a small mistake, you hit a mountain, that kind of thing. It's very useful, and thank you for that.
Yes, I think, sir, the algorithms itself are not a problem anymore, because we have, students are smart enough, and the panel, everybody here is well aware of what is the state of the art. I think what I'm just trying to send a message is that all this has to be put in the framework of system engineering and following a certain systematic and step-by-step approach, which will also help anybody that is developing such a system to bring them on the market soon enough rather than face difficulties. And such a mission, of course, I have chosen it because it is relevant in our context today, where we have really a requirement to provide transportation, VTOL especially, if it's very confined areas like Siachen. And the only thing is that we have to make sure that this development is done in a proper systematic approach, and then nothing is difficult. This is quite easy.
Thank you. Yeah.
Okay.
Thank you. It was a good presentation.
Thanks, sir. Thank you very much for your. So if anybody else has anything, you know, I have this email address and phone number. It's also on WhatsApp. So if feel free to reach out, and in case of any interesting collaborative activities, I'm also open to such kind of discussions or initiatives. At NAL, we are also working, as Kota sir rightly said, on the RPA and civil aviation aircraft. So we have all these efforts already ongoing at NAL itself.
I know, and especially with your expertise in the rotary wing, I mean, I hope, NAL actually starts collaborating more with HAL. Okay, so I'll also request Vijay Kumar sir to, see if HAL can actually exploit Omkar's experience, because he has done so much work for Airbus. It will be really nice to have, some collaboration between HAL and NAL. Both of them are in Bangalore and RWRDC.
Yeah,
Yes.
certainly. Actually, 7 years ago, I went to NAL, approached them to collaborate with us on the rotary wing.
Right,
And
right.
there was no one that did not take further. It's good that Omkar is here.
Right.
Let's see. I will also.
So we can take it offline. I mean, we can maybe just discuss offline with you. And I'm just here in Bangalore itself, so it's very close by for me to visit you also.
We will do that. Okay?
Yes, sir.
Thank you. Yes.
Thank you, sir.
Thank you.
So if there are no further questions, then we'll take a break now, because then we'll start in another half an hour for the remaining two talks. These are also very nice and exciting talks. I will first stop the recording here.